We will now review vector or cross product of two vectors. The cross product between vector A and B is the magnitude of A times the magnitude of B times the sine of the smallest angle between A and B, and it has a direction. This is the unit vector signifying that direction, and that direction is perpendicular to the plane formed by A and B. There are two directions that are perpendicular to the plane formed by vectors A and B. We will use a right-hand rule to determine that direction. So you take your right hand and put the fingers of your right hand in the direction of the vector A, and your palm faces B with the smallest angle between A and B, and your right thumb then points in the direction of our unit vector A sub n. Let's look at the cross product between different unit vectors in the Cartesian coordinate system. So let's first look at what happens when we take a cross product of a unit vector with itself. The magnitude of A sub x is 1, the magnitude of our second vector A sub x is 1, and the angle between them is 0 degrees, and then we have our unit vector. Sine of 0 degrees is 0, so this cross product will be 0. So the cross product of a unit vector with itself will be 0. Let's look at the cross product between A sub x and A sub y. So the magnitude of A sub x is 1, the magnitude of A sub y is 1, the angle between them, the smallest angle, is 90 degrees, and if you put your right fingers in the direction of x with your palm facing A sub y through this smallest angle, your thumb points in the A sub z direction. So the sine of 90 degrees is 1, so AX cross AY is equal to AZ. Similarly, you could show that AY cross AZ is AX and AZ cross AX is AY. Let's look at AZ cross AY. So the magnitude of AZ is 1, the magnitude of AY is 1, the angle between them is 90 degrees. If you put the fingers of your right hand in the direction of Z with your palm facing A sub y through this smallest 90 degree angle here, your thumb points in the minus x direction. So the unit vector is minus A sub x. So AZ cross AY is equal to minus A sub x. I want to point out that we will always be working with right-hand coordinate systems. So it's very important when you draw your x, y, and z axes that this condition here holds, that AX cross AY is equal to AZ. If you had instead drawn your positive x-axis like this, then when you took A sub x cross A sub y, you would have gotten minus A sub z. That means you would have drawn a left-hand coordinate system, and you need to always make sure you're drawing right-hand coordinate systems in this course. Otherwise, you're going to end up getting some wrong results. With what we know about taking the cross product of unit vectors, let's now write A and B in component form and take the cross product. So we first distribute this to get these 9 terms, and we know unit vector crossed with itself is 0, so these 3 terms are 0. Using the procedure we just looked at for taking the cross product between unit vectors, we could find these other terms, as shown here. and then collect your x component, your y component, and z component. So this expression is how you would find the cross product between two vectors written in component form in Cartesian coordinates. This is not an expression you want to memorize, but it turns out if you form this determinant where the first row are the unit vectors, the second row are the components of your first vector A, the third row is the components of your second vector B, expanding this determinant will give you this expression. Here are some properties of the cross product. It's not commutative, it's anti-commutative, it's not associative. Here's the distributed law. The cross product of a vector with itself is 0, and to verify any of these expressions, just write the vectors in component form and evaluate the two sides of the equations. Just like the dot product, the cross product is useful for writing equations describing physical phenomenon. Later in the course, we will look at forces on charges moving in magnetic fields. So here we have a magnetic flux density field coming out of the page, and we have a charge Q here moving with some velocity U. What we will find is that the magnitude of the force is QUB, and that the direction of the force is perpendicular to the magnetic flux density field and the velocity of the charge. This can be compactly stated as the force is equal to QU cross B.